the biggest number of all. Where does all this leave us? To the question, what is the biggest number in the world? What's the best answer we can give? As you will have guessed by now, it's complicated. For one thing, there are both finite and transfinite numbers, and it's hardly fair that they should be in the same competition. But even within the realm of the finite, when very large numbers are defined in completely different ways, it can be hard to gauge their relative size. To add to the fun, there's the issue of what starting assumptions we make. In other words, two set of axioms that we take to form the basis of our arithmetic. When we started our quest for the big number, matter seems clear-cut. We're all familiar with the number line, and it's easy at the beginning to tell which of two numbers is the larger. 10 is bigger than 1. 10 is bigger than 1. 100 is bigger than 10. A googolplex is bigger than Google, and so on. We quickly exhaust our ability to imagine big numbers, but that doesn't matter. No one can truly grasp in their mind's eye the immensity of a googolplex, but every child knows that a googolplex plus 1 is bigger than a googolplex. Relatively few numbers have special names. Some of these, such as Google and Moser, are invented, while others, like Skew's number and Graham's number, are not discoverable. They serve as useful markers as we venture further and further down the number line, but we rarely run into the problem of how we represent them. Exponentials work fine for the kind of ordinary big numbers we meet in everyday life or most of science. There are fewer than Gogol subatomic particles in the observable universe, and the Gogol is easily written as 10 to 100, where 100 refers to the number of zeros. If we were to write it out in full. The only numbers in physics or cosmology that put a strain on the family exponential form are those involving point-carry recurrence times for the entire universe. The times estimated for all the contents of the universe to return precisely to some earlier quantum state. The largest of these ever to appear in print is so much for the physical world. The numbers that are relevant to the circumstances of matter, energy, space and time in which we find ourselves. Circumstances of matter, energy, space and time in which we find ourselves. Mathematics, on the other hand, isn't confined to dealing with questions that are really relevant in nature. What's more, if we assume, as most mathematicians do, that there's a Platonic realm where mathematical objects exist outside of space and time, there's no limit to room available for writing any number in any form we like. Take Graham's number, for instance. We know that it's a specific positive integer and that it ends with the digits 195. The digits 195,387. We also know that it's just a power tower of 3, although a fantastically tall one. In the Platonic realm, free from any physical limitations, Graham's number is presumed to exist complete, now and forever, expressed in full, or as a power tower with all the trees stacked unimaginably high, or in any number form with care to represent it.
Problem is when we bring things over from this unbounded region of pure intellect and try to instantiate them in the real universe, we run into constraints. Graham's number can't actually be written out in full. It can't actually be written as a power tower of trees either. There isn't nearly enough space or matter in the observable universe to accommodate it in these expanded forms. In any case, if we're looking at it from a practical and human perspective, writing out gigantic numbers, even ones much smaller than Graham's number, in full would take up not only a lot of space and material, but an enormous amount of time. And what would be The point: no one would be able to make use of so much detail or mentally grasp it. In the case of Graham's number, you may remember we ended up calling it G64, which is nice and compact, but special names or abbreviations can only be given to a tiny handful of all the numbers that exist because there aren't enough meaningful symbols, letters, numbers, and so forth to go around. Also, whenever a certain representation is used, for it to be mathematically meaningful, it has to be backed up by a precise definition of what the number is and how, at least in theory, to calculate it. We discovered early in the book that the mathematical operations which, with which we're familiar from our school days, encoding count up by one, succession, addition, multiplication, exponentiation, are just the beginning of an ending hierarchy of increasing powerful mathematical actions known as the hyperoperator sequence. Beyond exponentiation lie tetration, pentation, hexation, and so on forever, each operation amounting to the repeated action of the of the one of the one immediately below it in the hierarchy. It takes some ingenuity to find convenient ways of representing these increasingly powerful operators when we move beyond exponentiation. It's easy enough to write 3 to the power of 4 as 3 to the 4, as we know that written out in full, this equals 81. But a more flexible sim is needed if we want to present, say, the extension of 3 by 4. One such sim is not up aroused in terms of which, for instance, 3 extended to the 4 is shown as. Despite its innocuous appearance, this number is far too big to be written out in full the real universe. Yet, as we learn, even the compact notations available for writing the results of hyperoperator sums are hopelessly inadequate when faced with anything as large or larger than Graham's number. Fortunately, help is at hand when apparatus and similar systems of notation are overrun. The trick is to harness a higher level of recursion or feedback so that the number of times a repetitive action has to be carried out isn't fixed at outset but becomes known only as the calculation unfolds. This leads to the concept of non-primitive recursive functions such as Ackermann's function and the equivalent sim introduced by John Conway chain around notation. Being all this in, being all this in mind, where do we stand in our journey towards the biggest number in the world? Let's put in order of size from smallest to largest some of the named big numbers we've met in this book, starting with 1,000,000, which we can just about visualize in its entirety. Imagine the crowd at a couple of Woodstocks and can easily write out in full. Up to this point, the ranking is straightforward. As we as we have to do this, if we have to do is look at the size of exponential and organize the numbers so that the power of 10 increases from one to the next. If the powers are stacked, then generally speaking, the higher the stack, the bigger the number. If the power are stacked, then generally speaking, the higher the stack, the bigger the number. Also notice that 3 of the numbers in the list are from the worlds of chemistry, physics, and cosmology, respectively, and 2 of these are estimates after the cosmic Poincaré recurrence time at the largest value ever referred to in a scientific paper. All the numbers going forward will be purely mathematical with no known counterpart in science. As we extend the list, we must also leave behind any familiar ways we learned about in Scholar for writing numbers, including scientific notation. We must abandon the use of exponents. Even stacked exponents of power towers become the numbers are simply too large to be represented in this way. Instead, we have to resort to arrow notations of their equivalents. The next three, the next three milestones We reach on our track to find the biggest number of all come from the work of Steinhaus and Moser and the system that involves writing integers inside polygons, nested polygons, and cycles. For the mega and megiston, we've switched the nuts we've switched to nuts up arrow notation because we've moved into realm of tetration and beyond. The mega is vastly bigger than anything we sensibly want to write in exponential form. Recall what a double up arrow means. A power tower of the number before the two arrows the height of which is given by the number after the arrow. So which is smaller than the mega is when the three dots indicate another 255 levels of 10. Clearly, the mega is heck of a lot bigger than down-page cosmic point carry recurrence time, which is only a bit more than 10 to up arrows 4.
We can tell at a glance that the megiston dwarf the mega because of the extra up arrow. Pentecting 10 to the 11 produce a number much bigger than the 10 to the 258, despite the fact that 258 is more than 11. If we were to write the megiston in terms of double up arrows, it would be where there are 11 tens in all, separated by double up arrows. This obviously far exceeds 10 to upper rows 257 or 10 to upper rows 258, between which the mega lies. But then we come to the moser with an immense leap in size, far bigger than anything that's come before. To calculate the moser, we have to operate a mega minus 2 number of upper rows. We've clearly entered into a realm of numerical giants that makes everything we've looked at before appear negligible and almost indistinguishable from zero. Moser is our current champion, to perhaps not for long, because next it must come up against the mighty Graham's number. In chapter 5, we build up Graham's number in stages, starting with G1, which is G1 is Hertz number by normal standards, the result of hexation, but is tiny compared with the Moser. After all, the Moser is calculated using a mega-2 number of arrows, whereas G1 involves just 4. But the next step in figuring Graham's number produces a monstrous jump, because G2 involves G1 number of arrows. The Moser uses fewer than 10 to up arrows 258 up arrows, and G2 uses 3 up arrows, 3 up of them. A hexation versus a tetration. It makes little difference the numbers being operated upon are greater. In the case of the Moser, the hexation wins by a very wide margin, so that G2 is much bigger than the Moser. We're only at the second step in the calculation of Graham's number and have already left the Moser far behind, with still another 63 levels to go. After evaluating each G number, that many up arrows are fed into figuring out the next G number until our intellects better into submission, we reach G64. Another way to appreciate the tremendous gap between the Moser and Graham's number is to express its terms in Conway's chained arrows. The Moser is less than 3 arrows 3, arrows 4, arrows 2, where Graham's number lies between. The value of that number in the sequence has an astonishingly powerful effect on the size of the chain as it's unpacked. Graham's number take take over as our new big number champion by huge margin, but again only temporarily. The sequence is generated very simply by the recurrence relation. So it's easy to define a number that's bigger than Graham's number G64. Just put n equals 65 factorial. This takes us to the next step in the G number sequence, in which we use Graham's number of upper rows to produce G65. Bigger still is G66 and much bigger is G Google. It doesn't take much in the way of creativity to keep naming larger and larger values for n so as to move even further along the endless line of G numbers. If you say G Google, I may say G googolplex, to which you might reply G Graham's number. These are fantastically large numbers. It's too much bigger than Graham's number, but they are all produced using the same mechanism or function as that used to generate Graham's number. They bring nothing new to the table, and so, in googological parlance, are mere salad numbers. Returning to our analogy with space travel, the quest to define bigger and bigger numbers is like the efforts to reach more and more remote objects in the universe in order to send spacecraft to other stars in reasonable amount of time, say somewhere between 10 and 50 years. With a propulsion system that can reach much bigger speeds than possible with chemical rockets. Plenty of ideas have been put forward for such systems, including a scheme called Project Daedalus, proposed in the early 1970s for a large uncrewed vessel, which would use a series of smaller nuclear fusion explosions to accelerate it to a nearby Barnard star, 6 light years away, in a journey lasting about half a century. To travel to more distant stars, thousands of light years away, or across intergalactic distances in sensible amount of time, something like the warp drive of Star Trek would be needed. Specific objects in space which lie at greater and greater distances, such as Pluto, Barnard star, the supermassive black hole at the heart of the Milky Way, and the Andromeda galaxy, are analogous to bigger and bigger spatial numbers, the Gogol, the Mega, Graham's number, and so on. The means of reaching these cosmic objects on practical timescale are, in mathematical terms, equivalent to the increasingly powerful functions needed to generate larger and larger number quickly. In all of this, there's a strong human element. In the case of interstellar travel, we'd like to get some results back within a few decades, and most because the length of time falls within a human lifespan. Voyager 1 and 2, already in interstellar space, will eventually reach the distances of the nearest stars, but not for tens of thousands of years, by which time the spacecraft will be long dead. If we were immortal, we might be content to wait tens of millennia to see close-up pictures from our robot probes of Alpha Centauri or the Sirius system, but our personal outlook and ambitions are based on timescale of less than a century. This same type of thinking transfers to mathematics and our efforts to reach greater and greater distance along the number line. It's commonly assumed that in some Platonic realm, all the numbers that can exist do exist, with all the digits laid out in full for eternity, and everything that's mathematically possible has a permanent home. This concept is reminiscent of the block universe of Einstein, in which all of space and time and all the events that have occurred or even will occur are portrayed as a complete unchanging four-dimensional entity, being human, and therefore with finite abilities and access to resources. We can glimpse only small parts of the Platonic realm of mathematics or the broad universe of physics. In the case of the physical cosmos, we use instruments of steadily increasing sensitivity and power and spacecraft of greater speed or technical sophistication to bring more distant objects into clearer view. In mathematics, to define and reach bigger and bigger numbers, we turn to faster and faster growing functions. We know that in theory, any number, however large, can be reached simply by counting up one at a time, just as we know that it would be possible to get the depth of the current observable universe by moving at walking speed. But we don't have a luxury of eternity in which to attain our goals in such leisurely ways. Now, in the mathematical case, the physical resources to store the result were finite beings, with a need for results on a human timescale. So in the search of bigger and bigger numbers, we look for ever faster methods for generating gigantic integers. The benchmark of such functions, as we saw in chapter 10, is the fast-growing hierarchy FGH, a family of recursive functions indexed by ordinal numbers, both finite and transfinite. The key property of this hierarchy is that the output from the function is fed back as the input to the next iteration of the function, and this repeated for however many times is detected by the ordinal index. In mainstream maths and geology, FGH is the gold standard for measuring the strength of other fast-growing functions and the relative sizes of the numbers to which these functions give rise. Often it's not easy or even possible to make a direct comparison using FGH as a benchmark for rival functions. Isn't as straightforward as measuring, say, distances with a ruler or the passage of time with a stopwatch. We can pinpoint, for example, exactly where Graham's number lies on FGH scale. However, it is possible to identify the first function in the hierarchy that indisputably surpasses G64 for a specific input. The reasoning runs like this: f omega is roughly on a pair with the Ackermann function, so that f omega plus 1 is comparable with the iterated Ackermann function. Graham's number is the same as 64 iterations of the Ackermann number A4, in other words, with 64 parentheses, from which it follows that the next computable number we look at in detail in chapter 10 was 3. This is the value of 3 function 3n arising from Kruskal-Walker's theorem for n equals 3. It represents a monumental jump in size from Graham's number. The smallest 3 could be its proven lower bound is more than a. So whereas Graham's number is equal to all the 64 iterations for A4, 3 exceeds and possibly far exceeds as to where 3 lies in terms of the fast-growing hierarchy. We know that it grows at least as fast as the FGH at the small Veblen ordinal, but it could be at much higher ordinal. Just as 3 is comprehensively larger than Graham's number, which is itself stunningly big, so the number known as SEG 13 is comprehensively larger than 3, like 3n. The subcubic graph function CGCN is a super fast growing function arising from the graph theory that was first defined by American logician Harvey Friedman. The specific value SEG 13 has been the subject of mass cosmological research simply because it demonstrably leaves 3 far behind in its wake. In fact, it's been shown that the minimum value that SEG 13 could take is with 33 sets of parentheses. Much bigger still than SEG is loader's number, the output of the winning C program submitted by Graph Loader in the 2001 Big Num Bake-Off competition, explaining exactly what loader's number is and proving that it was even SEG-13 would involve penetrating deeply into aspects of computer science. One of these is the calculus of constructions, which in turn is a development of lambda calculus, the mode of computing introduced by Alonzo Church in the 1930s. In the calculus of constructions, proofs can be put into the form of binary numbers and expressions written as power towers. The number that would eventually be produced if loader's program loader C were run on a computer with infinite memory is represented by D599. The function dn is a measure of how many expressions in the calculus of construction can be proved within approximately log n interference steps. The value of dn goes up very quickly as n increases because the calculus of construction is particularly powerful and expressive. David Moser was organized the Big Num Bake-Off showed that D99 is much bigger than on the fast-growing hierarchy. Loader's number is the output of and was both 33 and SEG-13 to become our the current champion. As the way SEG and loaders D5 lie on the fast-growing hierarchy, we simply don't know except that they far surpass the level of 33. The lower bound proves by most for loaders number of is incredibly weak and only chosen since it was enough to show that loader's number beat the second largest entry in the bake-off contest. Updating our list of named big numbers from smallest to larger, we now have as we move to the larger and larger numbers, it gets increasingly difficult to put them in order of size. The main reason for this is that they are defined in such totally different ways. Both the three SEG functions, for instance, arise out of graph theory. Loader's number, on the other hand, is the output of a program written in fewer than 512 characters in the C language to conform with the rules of Big Num Bake-Off, which takes every pattern of bits, ones and zeros up to some length and expresses this as a program in the calculus of constructions. It's possible to know anything specific about loader's number, such as how many digits it contains of what its final few digits would be if it could be written out in full. However, it is possible to analyze the code of the function at the heart of loader's number, dn, and thereby show that after the 5 nested recursion of d with n equals 99, d599 far exceeds SEG-913. In fact, in all cases, once we get beyond Graham's number territory, we rely on rough estimates of the growth rates of functions to help us determine the relative size of the numbers to which they give rise. We've come across in this book a lot of what might seem to be arbitrary numbers, such as 3 SEG-13. By note 3, 127 or SEG-42 or any other value that we might plug out of the air. The answer is that, having established the approximate growth rate of of function, it becomes possible to find the smallest specific input for which the function outputs a value that's demonstrable for an entire different magnitude to the output of rival functions. In the case of 3, there's a mind-blowing explosion in size from 33, 32 or 33, which makes 33 an instant member of the big number half of fame. SEG-13 then achieved stardom in gogological cycles. At any rate, because it's the smallest of the CGC sequences that can be proved to make T3 look funny by comparison. Another difficulty in ranking big numbers is that, frankly, relatively few professional mathematicians are interested in the pursuit. It's more of a hobby than a serious area of research. This doesn't mean that some very talented mathematicians aren't involved in gogology. If there weren't, no progress would be made at all. In fact, to truly understand what Loder's number, for example, is all about, call for graduate level grasp of computer science and mathematical logic. But it remains true that not much is published in academic journals on the relative size of very large numbers. For the most part, any peer review that takes place is confined to online gogology forums and the like. Despite all these challenges, we can confidently state the Loder's number is currently leading the field in our big numbers text. It's unquestionably true that Loder's number, Graham's number, CGG 1333, Loder's D5, isn't the end of the story, though not by a long way. There's the obvious point that D6, the next level of recursion, have a higher growth rate than D5 and that D9, D699, for instance, must inevitably be much bigger than D599. We can become even more tiresome and lacking in originality by agreeing in something like the googolplex Graham's number leaves Loder's original function in the dust. But nobody likes a solid numbers math like perhaps the void going down such an unavoidable route, we should refer to our current big number champion as Loder's number on higher outputs based on extensions to Loder's function. The same kind of generalization could be applied to all the fast-growing functions we've counted at 2 and to specific large numbers to which they give rise, but from now on, well, we take this as given. Loder's number is certainly one of the biggest computable numbers even defined, but the fact that it's the outcome of a finite terminating algorithm means that, in theory, it's knowable to any degree of precision. We can actually compute it because there aren't enough resources in the universe, but that's irrelevant. A Turing machine, which by definition has access to unlimited amounts of memory and time, could calculate Loder's number along with any of the other numbers on the list we've put together so far, as we saw in chapter 11. However, there are also uncomputable functions, the growth rate of which is guaranteed eventually to exceed that of any computable function. Among the best known of these uncomputable functions are the BC beavers, first described by Tiborado in the early 60s. Oddly enough, as we saw, a BC beaver is an incredibly inefficient computer program. In fact, that's the whole point. It's a program that takes the greatest possible number of steps to achieve a given goal. The corresponding BC beaver numbers, BBN, answer the question given a certain number of rules and what are the most steps that a Turing machine can take before it halts. The sequence of BC beaver numbers climbs a fantastic rate. BB2 equals 6, BB3 equals 107, and after the numbers skyrocket. BB6 is 7.4 times 10 to 36,534, and somewhere around BB17 the BC beaver sequence of the text Graham's number. Faster and faster the BC beaver accelerate until inevitably they overhaul Loder's number and any still larger computable number that we could ever define. No one knows for what value of an BBN overhauls D599, but for the sake of argument, let's say it's 1000, so that BB 1000 greater than Loder's number. The fact is, whatever number tops our list of computable numbers, there might be some specific BC number that is bound to exceed it. It's possible to extend the concept of PCBV numbers by supposing that there are super Turing machines that can solve that halting problem. These higher level Turing machines would give rise to an even faster growing sequence of super BC beaver numbers, which would in turn to be solved by super BC beaver numbers and so on. But this idea hasn't been well defined, and in any case is a mere variation on the underlying BC beaver theme. Holmes' iota function, which by definition would absorb every order function at every moment in time in the optimal way so as to generate the largest possible output, is novel but lacks any semblance of formalism. There's no way to analyze the iota function mathematically and remains little more than an imaginative suggestion and a philosophical exercise. This leaves just one number truly worthy of adding to the end of our list from the perspective of professional mathematics. If it's original in its conception, reasonably well defined, and utterly so stupendous in size, but common consent, it's one of the largest, if not the largest, finite numbers even conceived, and for that reason we're going to crown it ultimate champion, the winner of the big number duel on, and our nominee for the biggest number in the world is Gaius number R10 to 100. Augustine Gaius formal definition of his eponymous number involves about 10 lines of symbols and expressions in the language of set theory, and may as well be written in Chinese for anyone who hasn't gone deeply into the subject at university level. A simplified version of it runs along these lines: the smallest positive integer bigger than any finite positive integer named by an expression in the language of first order set theory with a Google symbols or less. Making some reasonable assumptions, this boils down to the assertion that Gaius function Rn across all other functions definable under the standard system of axioms ZFC used in most of modern mathematics.
For now, when it comes to the largest integers that we can sensibly talk about, Gaius number more or less marks the boundary with the unknown. Attempts have been made to define even bigger numbers with curious names such as Fish 7, Utter Oblivion, and Bigfoot. The last of these, announced in 2014 by a Googolist with the moniker Wojowo, uses a strategy similar to that used to construct Gaius number, but applied to a phenomenon that Wojowo called the OOD levels. To penetrate this world involve first learning the language of first order theory, an extension of standard first order set theory, a venture best tackled with a higher degree in maths and a right sense of humor. Unfortunately, it transpires that oddly theory has inconsistencies which render Bigfoot ill-defined, but Lode's number and Gaius number, which are at or near the top of our league's tables for the large countable and uncountable numbers, respectively, came about because of competitions. Maybe it's time for another contest to spark some brand new ideas. Until then, in the efforts to tread even further down the number line, Gogologists may need to rely on the same tricks used by Rayo, but apply them to beef up versions of first order set theory. Cosmologists strive to see more clearly to the edge of observable universe and find ways to learn about what may lie beyond. Mathematicians look to the farther limits of their own subject. Meanwhile, we can ignore any longer the elephant that's been sitting in the room since the start of this chapter. We know full well that the smallest of transmitted numbers, aleph-null, is bigger than any finite number we could ever possibly name. We know too that there are infinitely many alephs each infinitely bigger than the one before. Yet mathematicians can dream of cardinals whose size exceeds that of any conceivable aleph. To do this, they have to move beyond the usual foundations of their subject and resort to what are called forcing axioms, a technique pioneered by Stefan Klein mentioned earlier. This leads to the concept of modestly named last cardinals, which in reality are spectacularly vast, including those with special names such as Marlowe cardinals and supercompact cardinals. Finally, at least for now, there's a notion for absolute infinity, sometimes represented by capital omega, an infinity that transcends or surpasses all others. Cantor himself spoke about it, but mainly in religious terms. He was a deeply committed Lutheran whose Christian convictions occasionally surfaced in his scholarly work. To him, omega, if existed, could only do so in the mind of the God in which he believed. On that basis, omega is nothing more than a grand metaphysical speculation. Sticking purely to mathematics, absolute infinity can be defined rigorously, so mathematicians, unless they allow philosophical speculation to get the better of them, tend to ignore it. There may be the temptation to characterize it as the new number of elements in the universe of all sets, the so-called von Neumann universe. But the von Neumann universe isn't actually a set, rather it's a class of sets, so that it can be used to define any specific kind of infinity, whether cardinal or ordinal. More controversially, omega may be thought of as a sensible result if one were to be divided by zero. This isn't a procedure normally defined in a maths, though it can be done in certain forms of geometry, for example, projective geometry, which yield in the idea of a point at infinity or line at infinity. The case for omega will continue to challenge future generations of mathematicians, logicians, philosophers. Meanwhile, we have plenty of infinities. Infinity is infinitely larger than the one before to keep our brains occupied. What is the bigger number in the world? It depends on which world we're talking about. In that part of mathematical cosmos we've so far explored, we could sensibly answer a Yost number, but the future will hold many surprises and our journey into the limitless depths on the numerical cosmos has barely begun.